All right, continuing on with our KB examples here, we can see that in question number 2 here, or example number 2, we are given the pH of a 0.15 molar sodium fluoride solution to be 8.2, slightly more basic than the last problem. We have an initial concentration for ionic salt, which is going to dissociate into a couple of entities. Water will also be there, and we'll be able to identify a strongest acid and a strongest base for a proton transfer. Because we have pH, we have enough information to figure out our acidic or basic entities in the equilibrium expression that equilibrium equation that we come up with, and we can calculate the Kb. So let's do that one here. So you can see that if we go through this one, again, we have two compounds. You have your sodium fluoride and you have water, but sodium fluoride being an ionic salt will dissociate into sodium ions and fluoride ions. Water is our other entity here. So just be mindful of dissociation versus ionization again as we look at these ones. We go through it, and water is potentially an acid or base. Fluoride is the only other one you will see on your relative acid-base strength table, and it becomes the stronger of the two bases between that and water. So proton exchange is between water and fluoride. So we write our equation. And so fluoride ions exchange a proton with water in equilibrium to produce hydrofluoric acid, which is a rather insoluble molecule, and we have some hydroxide ion in solution. So there's our equilibrium expression, and we can go fill out our ice table here, starting with the 0.15 mole per liter initial salt concentration should be reflected in the 1-to-1 ratio of fluoride ions. Water doesn't play, and we start from 0 with both of our products here. You can see I've got this table already completed. I had to go through and do a few things. Remember, in this one we were told the pH is 8.20. Well, pH doesn't tell us the hydroxide ion concentration directly, but it can certainly be used to get there. So that's what we've got to do. If the pH is 8.20, then pOH 14 minus that value gives us a pOH of 5.8, which helps us get there a little bit more easily to our hydroxide ion concentration when we just run it through base 10 raised to the power of the negative pOH. 10 negative 5.8 gives us a fairly small value here of 1.584 times 10 to the negative 6. So we now have the hydroxide ion concentration for our ice table. We go through it much like we did the last example. All right, if I start at 0 and I finish at this, then that must be the increase. This, just like every other proton transfer solution that we have for these equilibrium systems, is a 1-to-1 to 1-to-1 ratio. All right, so that just means that the increases and the decreases would be the same throughout this equilibrium. Therefore, I have an equilibrium concentration for hydrofluoric acid that I can work with, and again, I have a 10,000 times difference here between 0.15 and 1.5 to the negative 6. So that satisfies my rule of 1,000 assumption. I'm going to ignore this change, just keep my numbers simple, and my equilibrium concentration is 0.15. So now I have the information that I need for my Kb expression. So I just go do my Kb. There's a percent ionization you can ignore. And so hydroxide, hydrofluoric acid all over the fluoride ion. These two guys are the same, hence it's that number squared like we saw in the last example. Divide by 0.15 and you get a small Kb value here of 1.7 to the negative 11. All right, identical to the last example that we had. Hopefully that one went well for you guys. There is one more example here on this section of the notes, and we're just taking a look at when given the Kb of this case. All right, we have the Kb for a weak base is 2.1 times 10 to the negative 6. We have the pH at 10.21. This one's a little bit of a different one. You're just working backwards through your ice table here to find the initial concentration of your base. We looked at one example like this in Ka as well. Your examples 1 and 2 are definitely much more like what you're going to be seeing throughout your quizzes and your homework questions. All right, so let's take a look at that one briefly here. So this is what we get to start with. All right, we have a generic weak base. It is reacting with water. We can create our two products in which water would have to be the strongest acid, especially if you have something basic here. And so the proton transfer goes that way. Your weak base picks up the proton, and water is stripped of it to leave just hydroxide behind. We're looking for, in this case, the initial concentration, so we're just really working backwards through our ice table here to solve the problem. All right, we were given the pH at 10.21, and so with a pH of 10.21, we can eventually resolve the concentration here of the hydroxide ion in solution equilibrium. pH equilibrium gives us the information that we need. So, here's the work that I would do. pH plus pOH is 14 again. This is generally the way that most of us will go through these problems. We just like the simplicity of this statement. And pOH is just 14 minus your pH to give us 3.79. That allows us to calculate the hydroxide ion concentration quite quickly. So we get it to 1.62 times 10 to the negative 4. I'd probably carry a few more digits here. I think it was just, oh, there they are. And so I have my equilibrium concentration. That allows me to go back and figure out the remaining parts. If this is 1.62, because of that increase, then this is an increase of 1.62 times 10 to the negative 4 to give me 1.62 to the negative 4 is an equilibrium concentration. This is a decrease of 1.62 times 10 to the negative 4. All right, so we don't have the equilibrium concentration for it yet, but remember, in this case, we were given Kb. So we do our expression, all right, your products over your reactant, but then I just do a little bit of algebra. I'm looking for my weak base concentrations. So I'm just going to multiply both sides by that concentration, divide by the Kb that this question provided. This is how this question is different from the previous two. So I can calculate the equilibrium concentration, that's this one right here, guys, for this weak base. All right, there's my equilibrium concentrations for the products, dividing by Kb, which was 2.1 to the negative 6 in this case, and we get 1.3 times 10 to the negative 2. All right, so now what we need to do is add this to the change to get back to our final concentration here. And so I'll just quickly plunk that into the calculator. All right, 1.3 to the negative 2 plus 1.62 to the negative 4. And so 0.131. When we round this to our 2 sig dig limit, we have, because of the pH number of 10.21, it stays at 1.3 to the negative 2. Okay, those are the remaining two examples that we had when pH, pOH, or Kb is given. It's really just bouncing around the equations just a little bit. Next video, we'll just take a look at what we do when we're being asked to calculate Kb, and pH and pOH are not available to us. So we have to look for other ways to get through the ice table.